Alrighty then, we are about to get started. But while we wait, let's play another round of Magic. This hand is kind of meh. I don't know. Yeah, this hand isn't really better. But I'm going to keep it. And I don't want you. Okay. I'm just hoping to draw lands. Yeah. What card you gonna name, opponent? I am strapped for the mana. Well, I guess that was a good draw. Huh. What do I do? I guess I play the Vasa. As they go. My opponent is playing what's called a stack strategy, where they're going to try to get me to sacrifice a bunch of permanents using Doom Foretold and etc. Kind of miserable to play. And he's going to bounce my Vasa. And then I'm going to have to sacrifice a Wolfwall Haven. So he's basically, in a way, playing land destruction against me. I'm trying to sacrifice. Okay. So what happens? All right, now you're going to have to play some permanents so you don't lose them. All right, time me, gain some life. Well, I can cook in a land. Then I can return. Okay, so you sack your Kaya. I'm just limping my way. I'm trying to keep this Doom Foretold from going off. But he's got a billion cards, so not like it's gonna matter. He has to have a sweeper. So even if I got my creatures out, he'd destroy them anyway. Go ahead and name your card. I don't think there's any way I can win this match. Maybe there is a way. Now it's time for class to start. So, excuse me. Okay, well, let's go ahead and Druida and see if anything happens. And I completely blanked. Wow. The odds. Well, I mean, maybe I know I'm not gonna hit anything on yours, but me, ooh. Let's go attacking. Okay. Let's Druida again. My graveyard. Okay, that's gonna play into Wrathing. This. I can surveil more. Hmm. Yep. The question is, ooh, how many Kaiserrafts have they milled? And I promise we'll be getting to dimensional analysis here anytime soon. There's one. So they've played one. I've milled one. Okay, so two of their Kaiserraths are gone. Blanked. They're gonna kill my Gerudo. Okay. Alright, I'm gonna get back. They exiled my Thassa. So I guess I'm gonna get back my Gerudo. So now, go ahead, bounce her back. Nope. Okay. Come on, let's spin that wheel. Let's deck him. Yes, Spark Devil. Come on, let's deck him. Oh man, the Forerunner. You're in trouble. Why can't they attack? Is there some rule? What am I missing? $13 cards to my 16 cards. That'd be funny if I could win by decking. Okay, how many brass? That's 1, 2, 3. 1, 2. Yep, that's 3. So there's one more wrath in the deck. I will discard this because it's worthless. He gets a 2/2. I draw a card. Let's spin that wheel. What do I get? What do I get? What do I get? My Thassa. Let's play my Fiddle Flip. Come on. Let me play a Fibble Flip. If you're wondering why it's taking so long to get to my rate conversion and dimensional analysis lesson, is that, well, no one's here. So it's all going to be on YouTube anyway. So I'm not keeping anybody waiting. That's a lot of triggers. Yeah, I'm going to get bolted to death. That was a good game. Miserable stacks, but they did win. Okay. So we'll play more Magic later, but not right now. Right now, we're going to get to this thing called rate conversion and dimensional analysis. So just so you're aware, dimensional analysis is something that sounds really complicated, but it's a great system for converting units of measurement. And it's something that I picked up in high school. I was in high school chemistry, and as soon as I wish I knew her name, she was this little short lady with a red perm, and she would climb up on counters. She was hilarious. But when she introduced me to dimensional analysis, it made converting measurements so easy that as soon as I hear the words, I immediately remember how it works. And I'm hoping it does the same for you guys. So basically, here's the kind of problem that we'd be talking about. Let's say you were given something like sound. Okay, so sound, and I'm pretending I'm making this up when I'm reading it. So sound waves travel at 5,120 meters per second. Okay, but let's say you had to communicate with another scientist or another engineer or whatever, and they wanted to know what is that measurement in kilometers per hour. Well, that's what we're going to be using dimensional analysis for today for rate conversion. So the way it works is you draw a line. Step one, done, draw a line. So step two, write down what you know. I know that I've got 5,120 meters per every 1 second. So that's what I know. Now I need to convert the meters into kilometers and the seconds into hours. So here we go using dimensional analysis, which is this method, this tool right here that I'm using. Okay, so meters into kilometers. Well, 1,000 meters is equal to 1 kilometer. Now you'll notice that I put the meters on the bottom, and that's because I need those to cancel each other out. Okay, so now I've got meters and meters cancel each other out. That's important. So what I'm left with, and this is a good thing, kilometers is something I wanted. Okay, so I'm gonna leave that alone. I'm done with that. Next, seconds into hours. Okay, well, 60 seconds, it makes 1 minute. And you'll notice, again, I put the seconds on top this time because I already had seconds in the bottom. It's like a big fraction. So those cancel each other out. Draw a line. 60 minutes are in every 1 hour. And again, I did the minutes on top because that would cancel the minutes. Oh, and you might notice all our units are canceled out except for kilometers and hours. So now, what you're going to do is get out your calculator. It's under all these things. I'll put it here. Let me clear this out. That should be the answer I'm going to get anyway. All right, so here's what you do. So the dimensional analysis tool is in place. I've got all my units canceled out, so I have the units I want, which is kilometer, yawning, which is kilometers per hour. Check and check. So then you go to your calculator, and you're going to multiply everything on the top and divide everything on the bottom. So I'm going to start with 5,120 right here, 5,120 divided by 1,000 multiplied by 60, and then times 60 again. So what we've just done is we've used dimensional analysis to convert the rate from meters per second to kilometers per hour. So apparently, the speed of sound travels at 18,432 kilometers per hour. And that is the demo for dimensional analysis for rate conversion. Okay, so now I'm going to take a look at some of the problems, but this is the skill that we're going to be using for today. So let's look at an actual problem, or at least another problem, because that was one that was just given. So I'm going to bring this calculator back in a little bit. But for now, I'm just going to clear all this out. Bring this guy over. The tool away. Zoom in a little bit. Okay. In 2016, the city of Rio de Janeiro had a population density of 5,377 people per kilometer squared. What was the population in density of Rio de Janeiro in people per square meter? Okay. I guess the reason you'd be asking this kind of a question would have to do with I don't know, some sort of political angle, like if you're trying to figure out, does a certain area need more facilities, or does a certain area need attention to its streets, or who knows, you'd be looking at population and population density. For instance, here in America, there are tons of people that live in major cities, but then you go to certain states like Montana, and you'll have very few people per square mile. Alaska. And these density calculations can help you understand, where your resources should be allocated. So let's go ahead and draw a line. That's how we start every one of these problems. We draw a line. Step 2, we're going to write down what we know. We know there are 5,377 people, P for people, for every 1 kilometer squared. Oh yeah, we separate each one of these by a vertical line. And we need this to be in people per meter squared. So people is already fine. So we just need to convert kilometers squared to meters squared. I'm hoping that's a simple 1,000. Let's see if it works out. So the squared is bothering me. All right, we're going to just hope and see if this works out. So 1 kilometer squared should be 1,000 meters squared. So kilometers squared cancels out with kilometers squared. So, well, we have people. We use a different color. All right, so we want people and meters squared. We have people and meters squared. So we drag the calculator on the screen, and what should happen is we start with, let's clear this out. So 5,377 divided by 1,000. That'd be 5.377 people. Oh, hang on, I lost it. 5 and 377 thousandths. Yeah, I was worried about that. That meter squared, kilometer squared business is bothering me. Let me try something. Let me back it up. Before I take a hint, I'm wondering if this is the case. So let's see if this comes out the same. All right, 1 kilometer squared. What color? Okay, so 1 kilometer squared would be 1,000. It's 1 kilometer by 1 kilometer. Let me try the picture. It's 1 kilometer by 1 kilometer, right? Okay. That'd be the same as 1,000 meters times 1,000 meters. Right. What am I missing? I gotta be missing something. I wish there were people here to chat and discuss with me. Per kilometer squared, 1,000 meters times 1,000 meters. I'm gonna be learning from my own mistakes today, because apparently my thinking would be divided by 1,000. It's still bothering me about the whole units being squared, but it's how we learn, right? So I'm gonna clear all my drawings. Yeah, it was gonna have to do with the area. All right, so let's go back to my drawing. So we're gonna draw a line, and I was right. We do 5,377 on top. But the fact that this is area, so when we say a kilometer squared, that's really 1,000 meters, like I was saying, by 1,000 meters. So in square meters, really 1 kilometer squared is 1,000 times 1,000. That was where my thinking broke. So 1,000 times 1,000 would be a 1 with 6 zeros. That's a million. So it's a million meters squared. That's the break. Square. Okay, so area is going to be a little bit different in dimensional analysis. Okay, so we still end up canceling out. So kilometer squared goes away. We're left with people and meter squared. So then we go to our calculator. We go to our calculator, and we do 5,377 divided by a million. and it's 0.00537. So 0.00537. Okay, so note to self. I'm hoping the next one's an area problem. Give me another area problem. Not this time. Okay. I'm going to mispronounce his name. So Uchi pumps gasoline at a rate of 18 liters per minute. What is Uchi's pumping rate at milliliters per second? Okay, so we're going to start by drawing a line. Then we're going to write down what we know. So I know that we're pumping at 18 liters per 1 minute. Okay, so we want to get to milliliters. Okay, so 1 liter is equal to 1,000 milliliters. Or is it 100? Centiliters would be 100. Milliliters is 1,000. So I guess there's some pre-knowledge you need to have here. So a liter is 1,000 milliliters. Okay. So I have that, and then seconds. Okay, and then 1 minute, and I have to do minute on top because my minute unit was on the bottom before, is equal to 60 seconds. So 18, I've got milliliters per second. So I'm going to get out my calculator. So that'd be, clear this out, so it'd be 18 times 1,000 divided by 60. So apparently it's 300 milliliters per second. Let's see. Sweet. Yeah. So when it's not area, it's really super simple. But I still want another area problem because I want to redeem myself. Yes. It's an area problem. Okay. So this is the chance to get this right. Okay, so I'm going to draw a line. So Rhea is applying mulch to her garden. She applies it at a rate of 250,000 centimeters cubed of mulch for every meter squared of garden space. Oh my goodness. Okay, let's write down what we know. 250,000 centimeters cubed of mulch for every 1 meter squared. Oh, really? Rhea is applying mulch to her garden. She applies at a rate of 250,000 centimeters cubed of mulch for every meter squared of garden space. At what rate is Rhea applying mulch in? Well, isn't this what she just? Oh, I see the difference. Never mind. So what we need to do is convert this to meters cubed. Oh, challenge. Okay, this is so we get to leave the meters cubed. I mean the meters squared alone. The centimeters cubed is what needs to change. Okay, so I need to draw a picture for this. And speaking of pictures, let me pull up my math practice standards. Oh, I closed it. Hang on. Excuse me. Okay. So, man, there's no good place to put this right now. Okay, I'm putting it up here. Okay, so right now what I'm trying to do is I'm just trying to make sense of this problem. And what I'm going to do, I'm going to make a model for my own brain. So this thing, this shape, 250,000 centimeters cubed. Okay. So here's my cube. I should, I've got a line tool. I should have just used it. Okay, so let's draw lines. Okay, so here's a line, 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 there's a line, there's a line. Okay, so here's my cube. Not perfect, but it's there. So we're talking 250,000 centimeters cubed. So what times what makes 250,000? Well, if I were to turn this into a scientific calculator, let's do third roots. If not, we can probably figure it out. Does it do any roots? Oh, it'll even do conversions for us. Nice. Okay. That's where the standard had the square root on it at least. Okay, so let's just start testing here. What's 50 times 50 times 50? Not enough. Looking for 250,000. 75 times 75 times 75. Too much. It's above 60. Oh, it's like in between 63 and 64. It's almost 63. Boogers. Okay. How do we proceed? This is the persevering part. $250,000 centimeters cubed into meters cubed. The goal was I was trying to figure out what each one of these measurements would be worth. But 250,000 doesn't cube down really well, apparently. Because 63 times 63 times 63 is just a little bit more than 250,000. I'm going to bite the bullet here. I think. Okay, so they're saying in my dimensional analysis what I could do. I can't downsize these anymore. Okay, let me move all this a little bit. Okay, so instead of me trying to figure out exactly what these measurements are for my cube, which would have worked, except that it doesn't come out exact. It doesn't come down to an exact figure easily. So what they're suggesting, I guess I should have thought of this, but oh well, learning. Okay, so instead I'm going to plug in a rate. So every okay. This right here. So I know that there's 100 centimeters in a meter. That's basic, but it's 10 to the third. So I'm going to cube them both. Okay. So the new volume. So there's going to be 1,000,000 centimeters cubed for every 1 meters cubed. So it's not important. I don't need to try and break this down and build it back up. I just need to plug in the rate. So the abstract thought here is that if there are 100 centimeters in every 1 meter, and then we were to cube both sides, well, 100 times 100 times 100, that's 6 years, that's 1,000,000. That's what they did to convert it. So that's their abstract reasoning for why there's 1,000,000. So then centimeters cubed cancels that centimeters cubed, and you're left with what we wanted, which is meters cubed over meters squared. So we will grab our calculator and do any old calculator will do. All right, so the 250,000 divided by 1,000,000, and it'd be 2,500, so 0.25. Okay, so plugging in the rate is much faster than trying to figure it out my way. I'm gonna open that one again. I do not feel, and this is the thing you guys should really be going through in your own learning process. Is like I understand it and I still messed it up, so I got to go until I can do it without getting any help whatsoever, and that's the perseverance part of this whole thing called learning. Okay, so whenever it's area and volume, there's a lot more thinking to be had. These other ones are like super duper easy. But plugging in those conversion rates for volume and area, a little more technical. Okay, so I'm gonna draw a line. The inclination tilt of an amusement park ride is accelerating at a rate of, okay, let's write down what we know. 2,160 degrees. We'll put a D for degrees over for every 1 minute squared. And I want this in degrees per second squared. Okay, so my brain is pinging a little bit. So let me go back to my math practice standards. I'm going to tell you what my brain is doing. Okay. So repeated reasoning. I'm remembering what the rigorous thing I just went through, and here's what I'm thinking about. I'm going to make an abstract right now. So let me try this. Okay, so Minutes and seconds. Okay, so we can agree that there are 60 seconds in 1 minute. I think we can all agree that. But I'm talking about second squared and minute squared. Okay, so if I was to square them both, that means that every one times itself is just one. So for every minute squared, 60 times 60 would be 3,600. I'm gonna sneeze, excuse me. Sorry about that. 60 times 60. 6 times 6 is 36. 10 times 10 is 100. Yeah, it should be 3,600 seconds squared. So that's my repeated reasoning, and I think I've just created a successful abstract. So So 1 minute squared is equal to 3,600 seconds squared. So the minute squared and the minute squared cancel out. So I'm left with degrees per second squared. So I'm going to take out my calculator and see if my abstract worked. So 2160 divided by 3600. Nice. And it worked. Learning is fun. Okay. So see if I can repeat. Let's see if I can repeat that process. A pitcher's arm rotates at a speed of 7 degrees per millisecond. Yeah, hang on. Let me write down what we know. A pitcher's arm rotates at a speed of 7 degrees per millisecond. Okay. So that's 7 degrees for every 1 millisecond. Okay. And I want in degrees per second. Oh, no exponents. So much easier. Okay, well, 1 millisecond based on the metric system is going to be 1,000 seconds. No, I'm sorry. Back that up. 1,000 milliseconds. That's right. Is equal to 1 second. That makes more sense. So the milliseconds cancel out. I'm left with degrees per second. So 7 times 1,000. I don't even need the calculator for that. So this should be 7,000 degrees. Sweet. The batting Wang Yu. Okay, I'm so apologizing. The batting Wang Yu Ying uses to fill quilts as a thermal conductivity rate of 0.3 watts per meter per degree Celsius. Okay. What is the batting's thermal conductivity value in watts per centimeters? Okay. Let's write down what we know. Let's draw a line. Let's write down what we know. So 0.3 0.03 watts per meter times Celsius. And it wants it in centimeters. Okay, well, 1 meter is equal to 100 centimeters, right? So meters cancels out meters. I've got centimeters. I've got Celsius. I have centimeters. I have watts. So it should just be 0.03 divided by 100, and that'd be 3/10,000ths, which is right. What in the world is that? Let's find out. A certain food has a gluten ratio of 13 milligrams of gluten per liter of food. What is the gluten ratio in micrograms per milliliter? Oh, that's a new symbol. I've never seen that, but it's something we can figure out. Okay, well, let's go ahead and dimensional analysis this thing. So we draw a line. Step 2, we write down what we know. Okay, so a certain food has a gluten ratio of 13 milligrams of gluten per 1 liter of food. And we want to know it in micrograms. That I'm going to have to look up. What is a microgram? I know this is a new symbol, but how many? E to the -6, apparently. Okay, so learn something new every day. So apparently a microgram is 1 times 10 to the -6th power. So what would that be? Okay, so if we've got, okay, hang on. So a milligram, okay, so 1,000 milligrams is 1 gram. Well, apparently 1 gram is equal to, hang on, back that up. Well, 1 times 10 to the -6. Okay, I might want to work that out. 1 times 10 to the -6. We take the 1, we back it up. 1, 2, 3, 4, 5, 6. Okay, so apparently point 1, 2, 3, 4, 5 zeros. That's 1, 2, 3, 4, 5. So this many grams is equal to 1 microgram, and that's that weird symbol. Okay, so let's back. Okay, so let's just check. So I've got 13 milligrams per 1 liter. I haven't even gotten to the liters yet. So 1,000 milligrams is equal to 1 gram, and 1 times 10 to the -6 grams is equal to 1 microgram. So far, milligrams cancels out milligrams, grams cancels out grams. So far, I've gotten that part. I still need to add on. So liters. So 1 liter. Thankfully, this is really easy. Is 1,000 milliliters. So liters cancels out liters. Okay, so do we have the correct units? We've got micrograms and we've got milliliters. Okay, well, let's see what happens. Okay, so 13 divided by 1,000, because it's on the bottom, divided by 0.12345 1, 2, that's 10, okay. Divided by 1,000 again, 13 micrograms per milliliter. Whew, we got there. So much unpacking in that one. First of all, you had to understand the dimensional analysis process. Then you had to understand, well, I had to look up what micrograms even were. It's 10 to the negative 6. That is a tiny, tiny thing. Then I had to put that into the dimensional analysis correctly. But my takeaways from today is I need to even practice more of the dimensional analysis with regards to volume and area, because the little conversion you have to do in between. But I do get it now because I had to practice, and that's what learning is. When you have something frustrating, you figure it. You get help by checking out the hints, and then once you check out the hints, you um, take those processes and you apply them to the next problem, and you learn. I feel smarter now. I wish some of you had joined me for the live session so we could have done this in real time, but hopefully you're all watching this on the YouTube channel later. Remember, your work is due by Thursday at 3 p.m. If you want correction notes, please get it back to me by Wednesday. For you guys, that would be 2 assignments that are on Khan. One is a quiz, one is not. Both you can try multiple times. So please get back to me if you have questions, if you're frustrated. This is good. This is good stuff. So I'll leave you with that, and I'll talk to you next time.